Dear organizers, dear participants, thank you for the invitation. My name is Yagub Aliyev. I am assistant professor in ADA University, Baku, Azerbaijan. I want to share the screen. So my topic is Conway type generalizations of the 3x+1 problem and p-adic representations of rational numbers. First of all, 3x+1 problem. It is one of the long-standing problems in mathematics number theory. Suppose x0 is a positive integer. For n greater than 0, we define recursively xn being equal to xn minus 1, the previous term, divided by 2, if xn minus 1 is an even number, and xn equals 3xn minus 1 plus 1 divided by 2, if xn minus 1 is an odd number. For example, if we will start with x0 equals 7, then we will obtain x1 equals 11, in the next step x2 equals 17, etc. At 11th step, we will reach x11 equals 1, after which it will become periodic, 1, 2, 1, 2, etc. Two problems about this sequence are still unsolved. First problem says that for any integer x0, for any positive integer x0, there is a number n such that xn equals 1. So eventually this sequence should return to 1. It is an unsolved problem. Second problem, which can look a little bit weaker, but it is also unsolved. It says that 1, 2, 1, 2 is the only periodic sequence that xn can generate. Of course, if we will consider also negative integers and 0 here, we have other periodic sequences. But essentially, problem 2 can be stated like this. Prove that there are only finitely many such periodic sequences that this recursive sequence can give. We will be mainly interested with the second question. Many famous mathematicians are associated with this problem. So this problem is sometimes called Syracuse problem. Sometimes the numbers that we obtain in this sequence are called Hale numbers because of similarity between Hale formation and the graph of these numbers. In some books, this problem is called Lothar-Collat's problem. He popularized it in conferences among his colleagues. Helmut Hasse also popularized this problem. Shizuo Kakutani and Stanislav Ulam are also popularizers of this problem. So this problem is sometimes called Kakutani's problem or Ulam's problem. Many famous mathematicians tried to solve this problem. Many mathematicians worked on this problem. American mathematician Murray Klumpkin worked on this problem, published some results. John Conway, who passed away recently in March, also published some results. Our today's talk is more close to his results, which are mainly about generalizations of 3x+1 problem and decidability. Coxeter, famous geometer, also published some results about this problem. Yakov Sinai, who is known for his work in dynamical systems, has also some publications about this problem. By the way, 3x+1 sequence can be interpreted as a dynamical system. Yes, simple system, but not trivial. This problem has connections with many branches of mathematics, including number theory, probability, statistics, algebra. So nowadays, this problem is not considered as an isolated problem. It is nowadays it is related to many fields of mathematics. There are some anecdotes about this problem. One is from Paul Erdős, who said, when he was asked by his students about this problem, mathematics is not yet ready for such problems. In another occasion, he said hopeless, absolutely hopeless. What he meant was probably that modern techniques of mathematics are not enough for the solution of this problem. The situation probably didn't change much today. Another anecdote is about Richard Guy, who is the author of this nice book, Unsolved Problems in Number Theory. He created a list of problems, published it as an article, with the following recommendation: don't try to solve these problems. Of course, this had only opposite effect, because many people started to be interested with this problem. But there is such a list, and there are reasons which are listed in the paper why these problems should not be tried. I just strongly recommend to read this article. A recent result came from Terence Tao in archive.org. Last year, he published this paper about 3x+1 problem, which says that almost all orbits of the collatz map attain almost bounded values. It is about behavior of this algorithm in the long run. It is a statistical approach, probability type approach. It is a very important result, but it doesn't resolve the problem. It is not clear at all how this approach will solve this problem. Anyone who is interested with this problem is recommended to read this book by Jeffrey Lagarius, The Ultimate Challenge, the 3x+1 problem. The book is kind of encyclopedia of all the previous attempts about this problem. And there are many interesting facts and theorems. Also, some information about false attempts. So, internet, there are some false attempts in the internet. You can look at these papers. Some of them claim to solve this problem completely. Okay. But mathematicians don't think that it is correct approach. So terminology and notation. I will need these notations. I will consider the set of operations tx equals x over 2 and sk. These are Conway type operations, 5x plus k over 2 for some k. There can be several such operations. So using these operations, I choose a sequence of operations, okay, p, b0, b1, etc., where repetitions are allowed. Suppose that the number of t operations, do you remember that division by 2, is n, and m is the number of non-t operations, all sk operations together. For example, this p equals s2t s1 is an example. I will generalize p by adding copies of it to the right and to the left of this sequence infinitely many times. So p will be interpreted as an infinite sequence, okay? Now I consider this equation. Suppose that given operations are applied to x in the given order, and then we obtain again x. So I want to find a periodic sequence, a number x which returns to itself after several steps. Of course, it is a linear equation and the solution is a rational number. I denote its solution by x0. Then I do cyclic permutation in the operations, put b0 at the end of the sequence, and obtain another equation whose solution will be denoted by x1. I do the same again, put b1 at the end of the sequence, and this new linear equation has solution x2. If I will continue in this manner, I will find many numbers. The last one will be xn plus m minus 1, which satisfies this equation. Okay, I will do the same with numbers xi, which I did with sequence p. I will extend these numbers, this sequence of numbers, to the right and to the left by putting copies of these numbers infinitely many times. I will also need these numbers ui, 2 to the I divided by 2 to the n plus m minus 5 to the m. These numbers will play a crucial role in the remaining part of the talk. So this number, the first of these numbers, u0, can be interpreted as a solution of this linear equation. Okay, this part is very important. So, there are integers, non-negative integers, kg, for which 5 to the k u0 plus minus uj is an integer. Okay. I'm mainly interested with kj, for which k is positive and k is minimal, in the sense that there is no other pair kg with a smaller k. Okay, this can be interpreted in a simpler way in the context of divisibility. Kg are the numbers for which 2 to the n plus m minus 5 to the m divides 5 to the k plus minus 2 to the j. In a similar manner, I can determine numbers k1, g1, for which 5 to the k1 ug1 plus minus u0 is an integer. Again, this can be interpreted in divisibility proper context. 2 to the n plus m minus 5 to the m divides 5 to the k1, 2 to the g1 plus minus 1. I will not now discuss why such integers exist. There are trivial pairs, there are non-trivial pairs. I will skip this part. It can be proved that there are infinitely many such kg, k1, g1. Also, plus and minus cases are considered separately, in the sense that k1, g1 determined for the plus case is different from k1, g1 determined for the minus case. Last notation, sigma SR, I will need this notation to state the theorems in a nice way. Sigma SR is the number of non-T operations in the fragment BS, BS plus 1, BR minus 1. Of course, sigma SS is equal to 0, because if the fragment is empty, then there are no non-T operations. Okay, I'm ready to state the theorem. If the pair of non-negative integers kg satisfy these, 5 to the k u0 minus ug is from the set of integers, then for the numbers xi, the difference is also an integer. Here I use that function sigma. So this is an interesting result. So essentially this says that xi have the same kind of property of being integer in differences as the original numbers u0, ug. The similar result for plus case. Okay, similar result, but this time the places of u0 and ug1 are changed. Again, numbers xi satisfy this property. And the last one, which is similar to the previous, the only difference is plus. Here it is also plus. So all these theorems say that although the numbers xi are rational numbers in general, in certain sums, in certain differences, they form an integer, which is surprising. I want to show one simple example. Take this sequence, which I mentioned before already. Here m is 2, there are 2 non-T operations, and n is 1 T operation. When I will solve this equation, I will get x0 equals minus 13 over 17. When I will do cyclic permutations in the operations, I will get other solutions, minus 24 over 17, which is my x1, and minus 12 over 17, which is x2. We also find the numbers ui equals minus 2 to the I divided by 17 for I equals 0, 1, 2, 3. we observe that the numbers ui satisfy these properties. So if you multiply, for example, u0 by 5 to the 6 and subtract from this product u1, you will get an integer. So k is 6, g is 1. It is a non-trivial pair kg. There are similar pairs for the other cases of the theorems. So I check that x0, x1 also satisfy corresponding properties in similar sums or differences. Okay, as you can see, sigma function sigma is present here. So to explain all this in a visual way, I used p-adic tools of Maple 2020. So this tool allows me to find p-adic 5-adic representation of those numbers. You can see them in the screenshot. I put these representations, these expansions, in the opposite way, like this. So everything is written in the opposite way, in the reverse direction. So the fact that 5 to the 6 x0 minus 5 to the sigma 0 1 multiplied by x1 is from the set of integers can be interpreted here as a repetition of the same digits in different rows of this construction. Okay, all these are the 5-adic representations of the mentioned numbers. So it doesn't matter where you put this. If you align them similarly, you always get the same repeating numbers, as you can see from here. The same for plus case. Here the repetitions, there are no repetitions. The opposite happens. If you add these numbers to these numbers, you will get only 4s, which means that it is an integer in p-adic in 5-adic representations. Again, it doesn't matter where you put them. It is always the same. Okay. 5-adic representations for the other cases, theorem 3 and theorem 4 are also given here. So I want to conclude with some points. There are invariants determined by the numbers ui, by which I mean k, g, and k1, g1, which are independent of the nature of operations in P. There are patterns in the p-adic representations which need to be studied more and in detail. These new mathematical objects need to be defined properly and investigated. Okay, my main motivation was to find all integer cases, in the sense that for which sequences of operations the numbers xi are integers. So here you see one such example, S3, S3, TTT. So the answer is the 3, 9, 24, 12, 6, 3. Indeed, if you will apply to these numbers, these operations in the given order, you will get return again to 3. It is not known how to classify all such periodic sequences. My references is the article of Lagarius, the book of Lagarius, which I already mentioned, and very useful and interesting paper by Conway on this problem. Thank you.